Hello everyone, my name is Aarti. I am from BSc Chemistry Honor second year. Today I am preparing a video for visually impaired students regarding the chapter Electromagnetic Spectrum of Absorption Spectra, that is infrared spectroscopy. Introduction. All compounds containing covalent bonds, whether organic or inorganic, absorb in an infrared region of the electromagnetic spectrum. In contrast, to a UV spectrum which contains only a few bands, in IR spectrum contains a number of peaks which provide a wealth of information about the structure of the compound. Therefore, IR is by far the most widely used spectroscopic technique for determining the functional group present in an organic compound. Units of IR radiation. The position of absorption in the IR region can be expressed either in the term of wavelength in micrometers or in terms of wave number, that is number of waves per centimeter, thus where mu is the frequency in hertz. However, most chemists prefer to use wave number rather than wavelength as unit, since the energy of radiation is directly proportional to the wave number, that is E is equal to h mu. The higher the wavelength, higher the wave number, higher the energy. Parts of IR. The IR region of electromagnetic spectrum expand from 0.8 to 200 micrometer. For convenience, it has been divided into three parts. The region which extends from 0.8 to 2.5 micrometer is called the near infrared region. That which extends from 2.2 to 15 micrometer is called ordinary infrared region. That which extends from 15 to 200 micrometer is called far infrared region. The near infrared region corresponds to energies in the range 11.44 to 55.75 kilocalorie per mole, while the far infrared region corresponds to energies in the range of 0.14 to 1.9 kilocalorie per mole. Since there are only a few absorption of organic compound in these regions, they are seldom used for spectroscopic night purposes. The radiation in the ordinary infrared region have energies in the range 1.9 to 11.44 kilocalorie per mole, which correspond to energy difference commonly encountered in the vibration states of organic compounds. Consequently, almost all the organic compounds show a number of absorption in the region, and hence this region is extremely useful to an organic chemist. Principle of IR spectroscopy. The absorption in the infrared region occurs due to excitation of molecule from the lower to higher vibration level. Since each vibration level is associated with a number of closely spaced rotational levels, IR spectra may be regarded as vibration rotational spectrum. We know that all the atoms in a molecule are not rigidly held but keep on vibrating to and fro about an average internuclear distance. Thus, each bond has a characteristic stretching and bending frequency. At room temperature, most of the molecule of a sample will be in the lowest vibration level. However, when ordinary infrared radiation are passed through the sample, some of the molecule will absorb a quantum of infrared radiation of appropriate energy and thus gets excited from the lower to next higher vibration level. In this higher vibration level, the native frequency of the bond remains to be the same, but in its amplitude decreases. Due to this increased amplitude, an oscillating dipole will be set up in the molecule. The interaction of this oscillating dipole moment with the electric vector of the infrared radiation leads to absorption of energy. When the excited molecule reverts to the original ground state, the absorbed energy is released as heat. Since the absorption in the IR region, like in the other region, is quantized, therefore only a selected frequency of the incident IR will be absorbed. As a result, each molecule will show a fixed number of peaks in the IR region. It may be noted that all the bonds in a molecule are not capable of absorbing infrared energies, even if the frequency of the incident radiation exactly matches the native frequency of the bond. Such vibration transitions, which are accompanied by a change in the dipole moment of the molecule, are called infrared active transition, and hence are responsible for absorption of energy in the infrared region. Conversely, those vibration transitions which are not accompanied by a change in the dipole moment of the molecule are not directly observed and are said to be infrared inactive transition. Molecular vibration. Type of fundamental vibration. We have stated above the atom in a molecule are not discretely held. They may be accompanied to a system of balls of different size connected to springs of varying strength. Here, balls correspond to atom and spring to chemical bonds. Just as we can compress and extend or bend a spring, in a similar way, bonds can be stretched or bent. As a result, there are two types of fundamental vibration for molecules, stretching and bending. In stretching vibration, the distance between the atom increases or decreases, but the atom remains in the same bond axis. On the other hand, in bending vibration, the position of the atom changes with respect to the original bond axis. These two types of vibration are shown in figure for AX2 systems such as NH2, CH2 and NO2. Type of stretching vibration: symmetric and asymmetric. Symmetric stretching. A stretching vibration is said to be symmetric if all the bonds are simultaneously stretching or compressed. Asymmetric stretching. A stretching vibration is said to be antisymmetric if one bond is being stretched while the other bond is compressed. Type of bending vibration: in plane bending and out plane bending. In plane bending, in these vibrations, the two atoms remain in the same plane of the molecule. These are of the following two types. In plane scissoring deformation, in this bending mode, the two atoms move toward each other like the blades of a scissor. In plane rocking deformation, in this bending mode, the two atoms move in the same direction to one side and then to the other side. Position of absorption band. From the equation of Hooke's law, it is evident that the frequency of absorption of a stretching vibration depends upon the following two factors: strength of the band or force constant of a bond, and the second one is masses of the atom form the bond or the reduced mass of the system. The third factor which affects the absorption frequency is the type of molecular vibration. Strength of the bond. Stronger the bond, higher is the stretching vibration frequency. We know that the strength of the bond increases in the order single, double and triple. Therefore, triple bond stretching vibration absorb at a higher frequency or wave number than double bond stretching vibration. Masses of the atom. The lower the masses of the atom forming the single bond or lower the reduced mass of the system, higher is the stretching frequency. The effect is particularly marked when one of the atoms forming the single bond is very small proton, which generally absorb in the region 3700 to 2630 centimeter per centimeter inverse. For example, OH bond absorbed near 305 3570 per centimeter and the OD bond absorbs around 2630 per centimeter. Hence, the strength of the bond are nearly the same, but the mass of an atom is double than that of other. It may be noted that in order to predict exact trends, it is essential to consider both the force constant and masses of atoms together. In some cases, if the predictions are made on the basis of masses of the atoms alone, we are liable to commit mistake. For example, on the basis of masses of atom alone, we would expect that the stretching frequencies would decrease in the order CH, NH, OH, FH, but in actual practice they increases. The reason being that the force constant increases in the order CH, NH, OH and FH. Thus, HF bond absorb around 4138 per centimeter, OH around 3570 per centimeter, NH around 3300 centimeter and CH around 3000 per centimeter. Type of molecular vibration. The frequency of an infrared absorption band depends upon the type of molecular vibration, whether stretching or bending. We have already discussed about the stretching vibration. of a group require more energy and hence appear at a higher frequency or the wave number than the bending vibration of the same group. Further, among stretching vibration, antisymmetric stretching vibration absorbs at a higher frequency than the corresponding anti-symmetric stretching vibration. For example, a symmetric stretching of a CS2 absorbs at around 2962 per centimeter, while symmetric stretching vibration absorbs at 2853 per centimeter. Similarly, different bending vibration of a CS2 group absorbs at different frequency or wave numbers, scissoring at 1465 per centimeter, wagging and twisting around 1250 per centimeter, while rocking vibration absorbs at 720 per centimeter. Thank you.